So historically, you know, this is a 2015 edition of this textbook, which, yes, let me complain about it one more time, okay? And it's just very similar to the previous edition, which I thought, oh, come on, give me some new figures, or, you know, give me. And they turned around, they basically swapped this chapter and the other chapter. So this chapter used to be before chapter 17, and now it's after chapter 17. So I just wanted to do it the same way I've done it. So that little blob there, so I'm a Star Trek junkie, just a little bit, and that reminds me of some of the Star Trek creatures that they interact with. Captain Kirk would know what to do with that.
Yeah, it does look like.
Doesn't it? Yeah. Well, and actually, it's later on we're going to see this figure too, and those lights are actually galaxies of stars, and so they're kind of showing you where dark matter is. Okay, it was the purple. Okay, so dark matter and dark energy. The thing they have in common is you can't see them. Dark matter, so that's like matter, okay, and dark energy, you think energy to do something, okay? Light bulb energy, okay? Dark energy. You can't see them, but we can see their influences. Or I can't, but astrophysicists and physical scientists can. So we know that they are at play, okay? Don't know everything there is to know about them. We're going to talk a lot about dark matter and a little bit about dark energy in this chapter. Okay.
You can't like physically see them, but you can just see their influence.
Right. You can see their influences. They would say kind of this sort of exotic sort of dark matter called WIMPs, weakly interacting massive particles, WIMPs. It's like, well, you guys heard about a few years ago about the whole, the God particle. What was that? Dang it. But anyway, what WIMPs do is basically they create gravity, but they aren't affected by gravity. It's weird. So sometimes, and I looked this up because I wanted to make sure I got it right, sometimes they call this normal material baryonic material, and that's this, okay? Atoms made of atoms. We talked about the structure of an atom. We have a nucleus and electrons outside. Within the nucleus, we have protons and neutrons. Okay, so normal matter, baryonic matter. But that doesn't add up to too much, okay? So it's weird how physical scientists actually will kind of take matter and energy and kind of say the universe is made of stuff and either falls in the category of energy or matter. Okay, so they kind of make 100% out of that. So breaking down into what the universe is made out of, we have a small amount of normal matter, a lot of dark matter, and a lot of dark energy. So let's go to our first, okay. So this is still our solar system, and this is another little applet to kind of change what we're looking at. So the way this works is basically I click on, this would be the orbit of Venus. This would be the orbit of, sorry, that was Mercury. This is Venus, the second one out. And the blue planet is the Earth. Okay, so what you're seeing is it slow down. Okay, and there's Mars. Okay, so this is actually showing it slowing down as you get farther from the mass of our solar system, which is basically our sun. So this seems a little random. This actually is a rigid object. This is like one of those, have you ever sat or put your kid in one of those little merry-go-rounds that was like a silver, kind of looks like a flying saucer? Okay, those things can make you sick. So basically, the way that works, since it's like one little rigid body, it's not mass that's kind of giving it necessarily rotational velocity. But if I go ahead and click a dot here, okay, kind of the closer you are to the center, the less you do, the less area you cover per rotation. Compare that to this one out here. Okay, you cover a lot of area per rotation. Let's go ahead and speed it up a little bit. Okay. So the farther out I get, okay, the faster my rotational speed. Okay, if I get near the center, okay, the slower it is. Okay, that's just kind of the rotational characteristics of a rigid body. Well, again, we're going to switch gears to actually how stars are moving in our galaxy. And definitely they're not all stuck like this, are they? Okay, so that is our galaxy, kind of looking at it face on. Okay. So let's take a look at how that works. Did you find Waldo?
These all are filled in.
Yeah.
We don't have
They're all filled in? Oh, okay, very good.
I was like, oh, all right.
Good. Well, stay awake now. I do kind of remember doing that. So I can click anywhere in there, and this is how the stars we know are moving in our galaxy. Again, looking at it face on. Okay, so close to the center of the galaxy, okay, they have a certain rotational speed. I'll kind of step out. They go faster as I kind of step out. Okay, and what we found is instead of like the outer planets slowing down, okay, the rotational speed just kind of flattens out. And I don't know if you can see how far out I'm getting, but actually I can go clear out here for the rotational speed of stuff. What that means is the fact that they aren't slowing down like the outer planets in our solar system slow down because they're getting farther away from the central mass of our solar system. Basically, the mass of our galaxy is just kind of, you're going to see it on the next slide. You can probably already see it. Basically, the mass is distributed even in the halo region. Okay, and actually, I think in Unit 1 we talked about where is most of the mass of our galaxy? In the halo region. What is it? Dark matter. Why is it dark matter? Because we can't really see it. Do we know it's there? Yes. We can see its influence. Okay? So that's what that is. Most of the Milky Way's mass seems to be dark matter. Specifically, it's located in the halo region. So this actually is kind of like we did with the sun, where I can start at the center of the galaxy and move out. Of course, we have that supermassive black hole in the center. Okay. And what we find is, okay, instead of the mass kind of bottoming out, it just keeps accumulating. Come on. Reset. Okay, and you know, if you think of when we talked about our Milky Way galaxy, one of the things you guys might have studied for this test is it's pretty thin on the outside, on the edge, isn't it? It's like 1,000 light years, okay, on the edge. So something's going on there. And let me draw one more circle, maybe a big long one. So there is mass out there that's not stars. Okay, it's dark matter. And actually, we're going to see dark matter could just be normal matter. It's just not lit up. Okay, or it could be something more interesting like these WIMPs I mentioned, weakly interacting massive particles. So this then is looking at the Milky Way galaxy kind of edge on, like we've done before. And if we look at how fast our sun is orbiting the center of our galaxy, we know that from the sun's orbit inward, that actually there must be about 1 × 10 to the 11th solar masses, okay, just because of the sun's motion. And that is, that fraction is a part of the total mass of our Milky Way, which is about 10 to the 12th solar masses. So if you do the subtraction, then that means that stuff that is not within the sun's orbit is about 9 times what's within the sun's orbit. Does that make sense? And to me, remember we said that we're actually, what did we say, 27,000 light years from the center. Okay, so we only have, what, 23,000 light years out to the edge, and it gets thinner. And there's all this mass that is not within our orbit. Again, it's in the halo region. So kind of what we've been talking about is this. Okay, so look at it carefully, and you can kind of see this sort of hazy stuff out here, somewhat drawn to scale. Okay, this would be the disk of our galaxy. This would be the official halo, and this would be maybe an extended halo. Okay? So what appears to be just a simple galaxy actually has an extension of dark matter, and we think all galaxies have this. Okay, it's quite significant. So this might look familiar to you. We said that actually you're like, because the next slide says that we can actually look at the rotation of stars in other galaxies and know that they have halos also. That in fact they have halos, but they have extended halos with dark matter in them. And this is how we can look at a galaxy if we're privy to kind of like the edge on, we could get the Doppler effect. So we have red shift, blue shift, red shift, blue shift. Okay, so these are all looking at rotational curves of stars around other galaxies. And they're kind of like the Milky Way galaxy. They kind of have this go up and they kind of flatten out. And that flattening out means that they're actually clear out there at the edge of where the stars are. You're still seeing matter added on, mass, I guess I should say. Mass coming from something, and if it's not lit up, it's dark matter. And this is saying that actually, not necessarily spiral galaxies, but even elliptical galaxies, we can get a fix on the fact that they also have dark matter surrounding them. So there are 3 ways of gauging the matter that's kind of hidden within a cluster of galaxies. One of the things we still need to talk about, again, is how galaxies are organized. Galaxies are organized in this feature called a cluster. And the Milky Way actually is a member of what's called the local group. It's a local cluster. But one of the ways we can just simply look at how they dance, okay? How they interact. We can use the Doppler effect to kind of see some galaxies moving toward us within a cluster, some moving away from us within a cluster, okay? And get a sense for that dance, and then we can get to the matter, that mass that must be strewn around. That's one way to measure the mass of a cluster of galaxies, or the mass that's hidden there. And so, for instance, in this particular cluster of galaxies, not counting, how do I say counting or not counting, the lit up part that's lit up by stars, there is 50 times the mass that these stars are, okay? So in other words, there's that baryonic mass that's coming from those stars, and then there's the dark matter mass, okay, that's coming 50 times that. So that's the first of 3 ways that we can go ahead and get to the mass of a cluster of galaxies. The second of 3 ways, that was our opening slide. Okay, so this is a cluster of galaxies, and actually we can take its temperature by using different wavelengths, get a fix on its temperature, and that actually we can translate, I can't, but somebody else can translate into the mass and where the mass is in that cluster of galaxies. And so again, we're seeing dark matter kind of between the galaxies within the cluster. So normal matter, about 15%. Dark matter, about 85%. Then this is my favorite. So this is the third of 3 ways. We can use they can use a technique called gravitational lensing. And do you guys remember when we talked about that objects actually create gravity because they make like a dent in the fabric of space and time? And and that's an Einstein thing, okay? And actually, you can see a star behind the sun, for instance, okay, because the sun makes a dent, and the light from a star actually curves around that dent. And that's what this is, okay, gravitational lensing. So basically, we have the real galaxy, just like it was the real star behind the sun. We have the real galaxy that's behind a cluster of galaxies. That cluster of galaxies making a dent in the fabric of space and time. So actually, we see the galaxy at two places. Okay, it's really there, okay, really hiding back there, but actually we see it come out and around, we see it here, and we see it come out and around, we see it here. Okay, the mass of that cluster of galaxies is making a dent in the fabric of space and time. The amount of dent it makes actually is an indication of its mass. That's a lot more mass than is really there that we can see. It's dark matter. So this looks familiar probably. Okay, there's a cluster, that same cluster of galaxies we've been seeing. But now pay attention to the little blue smears. Okay? And I have a video that I think is going to kind of show you how this works. But that little blue smear, it kind of looks like a clone of a galaxy. That actually is gravitational lensing of a galaxy that's behind that cluster of galaxies. If you know what you're doing, one of the things scientists can do with this gravitational lensing is they can use it to magnify distant images, just kind of like your lenses do. Okay? They can grab the light and concentrate it. So that's the same galaxy, just seen multiple places. That was the third of 3 ways of gauging the mass of a galaxy. Okay, so to kind of summarize, how do you get to the mass of a galaxy cluster, a cluster of galaxies? And so we talked about watching the dance, measuring the temperature, and gravitational lensing.
Do we need to write that down? Because I don't think that's on our video.
It's not on your
Got
handout?
1, 2, and 3.
Oh, it's not? It just kind of summarizes the... Good catch, Tina. Okay. Okay, so, you know, just mulling over, is dark matter, is it really dark matter that's, well, it has to be dark matter, or maybe we don't understand gravity. We don't understand how gravity influences the motion of objects, or the way objects, or light is bent around objects with gravitational lensing. And in dark italics at the bottom it says, no, we do understand gravity. We can anticipate a lot of things with regard to gravity. So gravity is in stone, so yep, there must be something out there that is acting like matter. It is matter, but we can't see it, so it's dark matter. So this actually is the Large Hadron Collider. And like the slide says, it's a 17-mile track. I think we've talked about this, the smash 'em up particle sort of thing, where basically you take a couple of particles, and I don't know if you zoom them around the track more than once, but if you don't zoom them around, or if you just zoom in a half a track, you basically send one this way, and then they smash up over there, okay? And you look at it's kind of like taking 2 cars, if you want to know what a car was made of, basically making a car fall apart, and then saying, oh, that's what a car is made up of. Okay, so basically taking parts of atoms and smashing them together. Higgs boson was the thing, and actually I think I have a thing coming up. This is the Higgs boson thing. The Higgs boson was the God particle that maybe was supposed to kind of help scientists understand a little bit what maybe dark matter is. So I'm going to click here, and so you can see a little bit what the Large Hadron Collider looks like.
amazing images there. Could we be entering a new realm of physics?
Are massive, massive compact halo objects. They just don't light up. Where are they? They're in the halo region around galaxies, and they're just very dense. And it could happen, right? It could be we talked about brown dwarfs, kind of failed stars. They wouldn't light up. But this actually, think I have a slide coming up that we think that there is some dark matter that's just normal matter. But honestly, and this goes back to kind of the Higgs boson particle, more than likely there are particles out there that are a little more exotic. That's WIMPs for short. WIMPs stand for weakly interactive massive particles. Okay. So when it says to me the best bet, my slides, it really should say both of these are in play. There's a lot of WIMPs and a little bit of machos. So this actually is the massive compact halo objects. Okay, like the failed brown dwarf stars. We do see them kind of running around, not running around, but this is showing some gravitational lensing that was done by an object that was not seen. Okay, and yeah, I can't really interpret this from left to right, but an object is going in front of that region and kind of magnifying the light behind it. You see it right there. Okay, so that would be your macho. So WIMPs have to be there somewhere, okay? And remember what scientists need to do is to basically take all their observations, and this observation actually can go back to kind of help what we're going to talk about next week, which is the Big Bang. Okay. So interactive massive particles actually could be a player in, this is a protogalactic cloud kind of getting started. We talked about basically a bunch of stars can be born, a little bit of rotation, and you got some disk to it, okay? But it could be that the dark matter around that protogalactic cloud was important for stars to be formed. So kind of after the protogalactic cloud, given, millions or billions of years, you got your disk of galaxy, your galaxy disk with stars in it, your kind of your globular clusters outside, and your dark matter remains. The dark matter doesn't collapse to the center, it just kind of remains kind of evenly distributed. So in the next couple of slides, actually, I'm going to show you kind of the distribution of galaxies. They're going to be little blue dots. But this is actually kind of showing you how galaxies are kind of gravitating together towards regions that we think are kind of some of these regions with a lot of dark matter. So kind of think, doesn't it look like one of those things where you had a filings and a little magnet and you can make this on that? Yeah. Okay. So this is showing kind of galaxies all gravitating towards these areas we think just kind of with a lot of dark matter present. So each of these dots is a galaxy, and it's kind of in 3 different sectors. So we are clear down here, okay, and kind of taking a wedge, I guess they're called wedges, taking a wedge out into the, pushing the edge of our cosmic horizon, okay? So this first part over here, okay, is actually this kind of string of, remember those dots are galaxies, this kind of string of galaxies actually is called the Great Wall. And it talks about the survey that kind of found that kind of set of galaxies. But can you see that there's a lot of blue in certain cases? Like there's gaps, and they're called voids. Okay, so this is kind of the, it's almost like a spider web sort of thing. And I've heard it kind of likened to actually kind of sponge it, like a sponge where a sponge has a pocket of air, and there's kind of galaxies kind of here and there. Okay, so there's kind of filaments of galaxies. Okay, and voids between those filaments. So going deeper, closer to our cosmic horizon, okay, we have another kind of filament of galaxies called the Sloan Great Wall. And it's kind of showing you how far back. So this is, so up there, when it says, like this, it says 1,200 million light years. So that would be, 1.2 billion light years away. That's how that works. Okay, so this one out here, 2.5 billion light years away. Okay, so this is kind of the distribution of galaxies. If you read the captions here, it says that kind of when you get to this third wedge, it looks like there's not as many galaxies, and kind of the answer there is up here. It says that there are fewer because it's harder to see them at those larger distances. You're only seeing the brightest of them. Oh, wait a minute. I guess there is a term on there. Sometimes when I'm looking for things to, because I think it's significant, there's this term down here, superclusters. So you have clusters of galaxies. The Milky Way is part of the local cluster, or the local group. And then you have superclusters. Okay, so superclusters are clusters of clusters. No, I could not find something better to call them. Yeah. So let's take, I know we're getting close, but let's take a break and then come back and finish those off so I don't have to ramble on. Okay, so about bottom of the hour or so, and we'll knock this out.